Yeah, I mean, it's yeah. Well, so I hope we go back to in-person conference again soon.
Yeah,
I mean,
hope things get better in time.
I was actually hoping with this one because it's the end of the summer and vaccinations, and I was hoping that this one would work, but in person, but I guess not.
Yeah, it's quite fluid at this point of time.
Yeah. Well, nothing we can do.
Yeah. Okay, so we have people joining us after lunch, and another 2 minutes to get started. All right. Hello, good afternoon, everyone. My name is Swapnil Ambade. I'm from University of Maryland, Baltimore County in the city of Baltimore. And I'm very glad to host this session. This is going to be a pretty busy session because we have some 11 talks. And as always, everyone keeps telling this for the sake of time. Just have to be very careful with the clock. And another 1 minute or 5 seconds, we're going to hear first from Dr. Gerd Grau from York University, and he will be talking about his work on smart carbon fiber composite structures utilizing printed electronics. Over to you, Dr. Gerd.
All right, thank you for the introduction. So my name is Gerd Grau from York University in Toronto, Canada. And today I'm going to talk about how to create smart carbon fiber composite structures by using printed electronics, using printed electronics as a method to interface with carbon fibers and turn them into smart structures. So before I get started, I want to acknowledge and thank my students. They do all the work in the lab. And for this work that I'm going to present today, especially these two here, Mohammed and James, they did most of the work. And also, I want to thank our funding and our collaborators. So first of all, what are carbon fiber composites? They obviously use carbon fibers that start out as bundles of fibers or tows like this, which we can then weave or braid into textiles. And so these textiles, they're strong in tension, but they're not strong in shear, they're not strong in compression. So if you want to have an actual rigid structure, a 3D structure, you need to mold it into a 3D shape, and you need to infuse the carbon fiber textile with a matrix, for example, an epoxy, and then you can create something like this, like an airfoil structure, for example. So carbon fibers are becoming more and more prevalent in a lot of different applications because the cost has come down. I mean, it's still expensive, but the cost has come down. So now we see it in aerospace, automotive, healthcare, structural engineering. And in all of those applications, really what we're using is the high strength to weight ratio. So we can create very strong, very lightweight structures. And carbon fiber has a couple other advantages. One that we're going to use today, or we're going to use in our work, is the electrical conductivity. So we can actually use the carbon fiber itself as part of an electronic or electrical system to create smart structures. And one of the big drawbacks from carbon fiber composites is that they're complex. So it's not just a single material, it's a composite that consists of a textile, multiple fibers crossing over each other, with that resin embedded in it. So it's difficult to predict the failure mechanics of these structures. So rather than predicting the failure mechanics, what people like to do is actually monitor those structures. and figure out what are the strains. Is there any damage in the structure? Do we need to do any maintenance? And there are different ways to do that. One is to use external methods, for example, acoustic, eddy currents, and that works well. But the problem, of course, is you need external equipment. So you need to apply that external equipment. You need people to do this. And you can't just do it in service all the time, typically. So, so if you want to do that, then integrated monitoring is the way to go. So basically, we take sensors, we put them on the structure or into the structure, and then we can continuously monitor, for example, if there's any damage, if there's any strain. And so you can use, for example, strain gauges, optical sensors. And the problem there is then if you want to have sensing over a very large structure, just imagine, for example, an airplane structure, and you want to monitor strains all over that structure continuously, you need a large number of sensors. So you need a lot of, it's a lot of cost. You need to put in a lot of labor to put these sensors in, but also you might even disrupt the structural integrity of the structure if you put in too many sensors. So ideally, what we want is a technology that can integrate electronics directly into a CFRP structure without disrupting sort of the traditional manufacturing, the traditional structure. And what we propose is that printed electronics can do that. So printed electronics has been around for a few years now. And what it is you use traditional printing methods like inkjet printing, screen printing, gravure printing, offset. All those different techniques have been proposed and have been studied. And you use that not to just print color, but to print electronic materials. So you can print metals, semiconductors, dielectrics, all sorts of active materials to make devices like transistors, sensors, and so on. And really the benefit of printed electronics is that you can fabricate electronics over large areas. So you can have substrates that are centimeters or even meters in size, and you can do this at very low cost. So that's really the difference to traditional microfabrication. And printed electronics is very good if you have a large area substrate. You need to fabricate electronics at low cost over these large areas, but you don't have a high density of devices. So not like your CPU, for example, because then you can get actually low cost overall. And what we propose then is that in addition to traditional applications like flexible electronics, variable electronics, carbon fiber structures might be another good application realm for printed electronics, because integrating, for example, sensing or other functionality into carbon fiber composites really fits that bill. You have a large structure, you want to put electronics into it. It doesn't have to be the highest performance, it doesn't have to be the highest density, but because it's such a large area, you want to have low cost per unit area. So printed electronics can give you that. And then the added benefit is the carbon fiber itself is electrically conductive, so we can actually use it as part of our system, for example, for sensing. So to do this, we developed a process to print a conductor onto a carbon fiber sheet. And what we do is we actually print on the dry carbon fiber textile. So before it's been infused with epoxy, that allows you to print onto a 2D structure, which is easier than onto a 3D structure. And we use paste extrusion or dispenser printing. So basically you have a nozzle, you have a high viscosity paste, you extrude it through this nozzle, and then you translate your nozzle relative to your substrate to generate whatever pattern you want. So we use this because it has a high viscosity. That means the ink doesn't get absorbed into the textile. It doesn't spread uncontrollably over the textile, which could be the case with inkjet, for example. But the problem is we need to be in close contact with our substrate here, and this carbon fiber textile it's not a very fine textile. These bundles of carbon fibers, they have 3,000, 6,000 fibers in them, so they're fairly rough, they're fairly thick. And you can see here in this sort of side view cartoon, you have these fibers or these bundles of fibers going into the page and running across. And so the problem is that this nozzle can get entangled with stray fibers. So we have to increase the standoff distance between the nozzle and the substrate. And so we have to optimize and understand the printing parameters that allow you to still print in these challenging conditions. But let's say we've optimized this and we can actually print the silver. So now we have silver printed on our carbon fiber. We can cure it. And then from then on, we can just use traditional carbon fiber composite manufacturing techniques. So we can infuse it with epoxy, and then we can, for example, compression cure. We've used vacuum bagging as well. So you can use traditional methods to then finally create this composite. And you just have to melt off the epoxy on top of the silver. And now you have a good contact between the silver and the carbon fiber. And then, for example, you can print more silver or other materials to create a circuit, and your carbon fiber is part of this circuit. And so this here would be then the final composite, and you can see these silver electrodes here. So we looked at a couple of different applications. One was a self-heating carbon fiber composite. So we molded this wing structure here. We printed these silver contacts on top, and then we ran a current through it to create basically a self-heating wing for de-icing. Since we're in Canada, ice is always on our mind. And you can see then if we run a current through it after optimizing, the geometry, resistance, and so on, we can get heating in excess of 100 degrees C. So that's plenty for de-icing. But you have to be careful, for example, taking into account the structure of the carbon fiber. If you do this with these unidirectional carbon fibers here, where all the fibers run in one direction, they don't cross over each other, then the heat can't spread out, and you get this non-uniform heating. If you have a twill where fibers actually cross over each other, you get much more uniform heating here. We also use this to detect damage and strain in a carbon fiber sheet. So we printed some current electrodes. So we inject current here into our sheet, and then we can measure voltage at different points in the sheet. And you can see from this modeling, if we have puncture damage, for example, this rectangle, we also looked at smaller damage, but you can see that it disrupts the potential, and then you can measure this as voltage. And we designed an interface circuit, and that allowed us to actually detect where the damage is inside this carbon fiber sheet. So these two applications so far have been only silver directly on the carbon fiber, but we also looked at a slightly more complex device, and that is a light-emitting carbon fiber composite. So imagine you have a carbon fiber structure that you want to light up at night, and that can be, it can be for aesthetic reasons. It can be for safety reasons, just visibility. But even more interestingly, you might be able to use this for structural health monitoring as well. So imagine you have a carbon fiber structure and you want to know, is there a lot of strain in the structure? Where do we have strain? Or do we have damage somewhere? So maybe there's a crack forming, a fatigue crack that if you catch it early, you can do maintenance or maybe change the part before there's a catastrophic failure. If you have a light emitting structure where if the light goes out in a certain region, you can tell I have to do maintenance, then that makes monitoring much easier than if you actually have to go in and measure in detail if there's any damage anywhere. This can be done with a simple camera, for example. So we developed this electroluminescent CFRP then, using a fairly simple structure, a capacitive structure with 2 electrodes and then a dielectric in between. And if you apply an AC voltage between your 2 electrodes, the dielectric phosphor will emit light, and it goes through this transparent or semi-transparent electrode here. So electroluminescence, of course, is not a new principle, but we showed here that you can do this with a carbon fiber compatible manufacturing process. So the bottom electrode, which is opaque, is a carbon fiber twill. So this is your actual structural carbon fiber. That's one of the electrodes, which means you don't need to fabricate this electrode with another material. So you save cost, weight, and so on. But also we can then use this to monitor the state of this structural carbon fiber to see, for example, if there's a crack in it or any other damage or strain. The next layer, the dielectric phosphor, is the same epoxy we use to infuse the carbon fiber with, and it's loaded with these phosphor particles that emit light. We plate coat it. And then finally, the semi-transparent electrode is, again, carbon fiber. It's a veil. It's commercially available, so you can lay it up the same way as the other carbon fiber layers, infuse it with epoxy. It only lets about 50% of the light through, so that's a problem maybe, but it's all compatible. It's simple processes, so you can directly integrate it into a carbon fiber reinforced polymer process. And so here you can see we get a nice light output after some optimization. And in this cross-sectional view, you can see the structural carbon fiber, the phosphor, and the mesh. And so we did a uniaxial tension test. You can see that we have a standard stress strain curve, but as our strain increases and stress, of course, our light output decreases. So you can actually then visualize the strain by seeing if your light output changes. And once we hit the failure point where the stress just drops, our light output also drops. So you can see this here. This is with 0% strain. And after we observe failure, you can see two things. One is here in this region, our brightness has gone down, but also at the bottom here, this complete area is black because we have a crack. So the sample has failed, and you can actually see that the sample has failed. You don't need any sophisticated sensor or monitoring equipment or anything. You can see that it has failed visually. And so this decrease in illumination happens because the resistance increases as we strain our carbon fiber composite. So you can do this in a uniaxial tension test. You can do other tests. We've done puncture, but also we've done bending tests. So here, for example, when we applied a large force, the whole sample basically cracked, and you can see all the light is off except here in the corner close to the contact. We also did a fatigue test. You can see this crack has spread over some cycles, and you can see actually here this crack is basically a black area, so you can see where the crack is, and then maybe you have to do something to your sample. So with that, I'd like to conclude that carbon fiber, structural carbon fibers in a composite can be used as an electronic material, so they can be used as part of an electronic system to create a smart structure. And we can do this using standard composites manufacturing technology by integrating it with printed electronics. And that can then be used for a bunch of different applications, for example, self-heating, strain damage detection by resistance measurement, but also optically by light intensity variations. Thank you very much. Are there any questions?
Okay, thank you, Dr. Grau. It just exactly 15 minutes. Just for the sake of time, if we could take questions a little later, we can just move to the next presentation. So thank you very much.
Thank you.
Okay, next is from Dr. Longwen Tang, and he will be talking about fracture mechanics of phase-separated classes by fluidodynamic simulations. Is Dr. Tang here? Okay. Okay, so I don't see Dr. Tang here, and nor do I see any of his videos. We can move to the next talk. And do we have Dr. Castle, Dr. Xavier Castle? Okay. Let me check. Yeah, so I do have his video, and what I can do is I can just share his video and we can get moving.
I am Xavier Castel. I'm speaker.
Okay. And also share the sound. Okay. So here we go.
I am Xavier Castel and I will speak about my work on sandwich structures composite materials for Wi-Fi antenna application. This work has been carried out in the multifunctional materials team at the Institute of Electronic and Digital Technology, University of Rennes 1 in France. My talk will be divided as you can see. First, I will introduce the context and issue of this study. Then I will speak about the antenna layout, the characterization of the carbon fiber tissue, and of the composite panel used to fabricate the full composite antenna. At last, I will present the microwave performance of such antenna for Wi-Fi application. Air or sea or land carriers need microwave antennas to ensure communication with their environments. So many antennas are attached to the surface of their composite panels, such as on this plane or on this mine hunting vessel. Metal sheets will be used as radiating elements directly embedded inside such composite panels, but it would have a strong impact on their mechanical integrity. Some alternatives were investigated to replace the metal by conductive materials suitable with composite materials such as conducting polymers, conducting injects, textiles coated with carbon nanotubes. Our study here concerns the use of carbon fiber tissue as a replacement for metal in view of the fabrication of full composite material antennas in order to preserve the mechanical properties of the composite panels. But what about the microwave performance of such antennas? We fabricate a reference counterpart with radiating element, feeding line, and ground plane made of copper sheets, all of which embedded into the same sandwich structures composite panel to compare the performance of both antennas at microwaves. The layer selected here to assess the full composite antenna for Wi-Fi application is a slot-fed patch antenna because it is easy to fabricate with the composite materials. The radiating element is a single square. There is no direct electrical contact between the feeding line of the antenna and its radiating element. The basic framework inspired from the work of Posa with a radiating patch fed by coupling through a slot made in the ground plane. Patch and ground plane were splitted from each other by an air gap with a control height. Transposed to composite materials, the patch in carbon fiber tissue or copper sheet is set apart from the ground plane here with a slot through honeycomb with a control height. On the backside of the ground plane in carbon or copper, there is a feeding line here in carbon or copper too, placed on an LTEC substrate here, which feeds the slot and thereby the patch. Each part of the antenna is brought through e-glass fiber and epoxy resin prepreg tissue here, 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 and here, used as a radome to protect the radiating patch. The size of the patch is set at 35 mm to 35 mm to answer the Wi-Fi operating frequency of the antenna, close to 2.5 GHz. Now, let's move to the electrical and dielectric characterizations. First, the electrical characterization of the carbon fiber tissue with the 4-probe setup. As expected, the sheet resistance of the carbon fiber tissue is larger than that of the copper sheet, but its value remains satisfactory in view of microwave applications. Electrical conductivity of both samples was computed from the formula here, relating the sheet resistance value, the conductivity, and the sheet thickness. It is worth noting that the ohmic resistance of the radiating element is equal to the sheet resistance of the tissue due to its square shape. It is not the case of the feeding line. The dielectric characteristics, namely the relative permittivity and the loss tangent of the e-glass fiber epoxy resin prepreg and of the honeycomb, were performed by the stop perturbation technique at 1 GHz. Those of the Neltec substrate were provided by the supplier also at 1 GHz. As expected, the dielectric characteristics of the honeycomb are very close to those of the air. Afterwards, the two sandwich-structured composite antennas, a full composite antenna with carbon fiber tissue and the reference one with copper sheet, were fabricated by molding prepreg tissues. First, two plies of e-glass fiber epoxy prepreg were laid on a glass slab. The Neltec substrate with the feed-in line in carbon or copper on one side and the ground plane with the slot on the other side is placed above. Then, two plies of e-glass fiber epoxy prepreg, the honeycomb, two other plies of e-glass fiber epoxy prepreg, the radiating patch in carbon fiber tissue or copper sheet cut to the required size, and at last, two plies of e-glass fiber epoxy prepreg for radome. Both samples are compacted under vacuum with a plastic bag and cured at 120 degrees for 40 minutes. Here are the pictures of the different layers of the sandwich-structured composite antennas in copper and carbon with the feed-in line on the Neltec substrate and the ground plane with the slot. The honeycomb. On this, two plies of e-glass fiber epoxy prepreg and the radiating patch in copper or in carbon. On the final sandwich structured composite antennas, the rear side and the front side. Let's move to the microwave performance of such antennas for Wi-Fi application. Both antennas, the reference one and the full composite antenna, exhibit an operating frequency close to the Wi-Fi band, with similar radiating patterns here. As expected, the full composite antenna exhibits lower gain value compared with that of the reference one, mainly due to ohmic loss in the carbon feeding line. Carbon is not a metal. Nevertheless, with a measured gain equal to 3.6 dBi, the full composite antenna is fully operable for Wi-Fi application. In conclusion, the use of carbon fiber tissue as replacement for metal in view of full composite antennas has been investigated. Relevant microwave performance at 2.5 GHz has been measured, and thus, such full composite antenna is fully operable for Wi-Fi application, associated with high mechanical strength, lightweight, and corrosion resistance. In closing, I would like to thank very sincerely our financial supports, the European Union, the Ministry of Higher Education and Research, the Brittany region, the Côte d'Armor Department, and the city of Saint-Brieuc. And you for your kind attention.
Right, that's interesting. So we'll move to the next talk. And do we have precaution live? Okay. And I don't see her. Okay, I don't see a video either. Then we may probably have to move to the next talk. Do we have Dr. Leonard Love? Okay, if it's not there, I probably have the video. No, I'm sorry. Okay, do we have Dr. Shao time? Okay, if not, then we have the video. I can just play that video right away. So this is about cellulose nanocrystal biopolymer hybrid bioink formulation for high resolution 3D printing of heterogeneous tissue constructs. So let me quickly share that video with you. Oh. Okay, can you see this? Can you see this, everyone?
Yes, we can see it.
Okay.
My name is Yun
Here we
Ying,
go.
postdoc in University of Waterloo in Chemistry Department. It's my distinct honor to be giving this talk at AAAFM UCLA conference on cellulose nanocrystal biopolymer hybrid bioink formulation for high-resolution 3D printing of heterogeneous tissue constructs. 3D bioprinting is a technique for assembling biological materials in complex layout that mimics native human tissues. It reveals promising leads in the field of tissue engineering, such as skin, liver, kidney, etc. In our group, we selected micro-extrusion-based bioprinting as the printing technique due to its ease of use and the compatibility with multi-material printing. The essential aspect in 3D bioprinting is the development of optimal bioinks. As the biomaterial for tissue engineering, several criteria need to be met, including hydration, mechanical property, biocompatibility, and biodegradability. Ideal bioinks must also meet the requirements for printability, such as resolution and pattern fidelity. Bioink with strong shear thinning is preferred. The low viscosity at high shear rates prevent clogging and shielding cells from shear forces within the nozzle that can lead to cell damages. Once through the nozzle, the shear rate decreases and the ink thickens up again to hold its shape. In addition, the elastic modulus G prime should be higher than the viscous modulus G double prime, as it avoids spreading and collapsing. To ensure high structural integrity and long-term shape fidelity, in situ cross-linking and instant gelation after deposition are also preferred. Therefore, suitable bioinks can be natural biomaterials, synthetic biopolymers, or the nanobiomaterials. In our group, we first selected arginate and cellulose nanocrystal as the bioink formulation. The dimension of the high aspect ratio CNC from the TEM image are 200 to 400 nanometer in length and 10 to 20 nanometer in diameter. It's a very promising nanomaterial in bioprinting due to its optimal mechanical and rheological properties. We found that pure 2% arginate hydrogel showed a porous structure with a pores in the range of 7 to 178 micrometer. But the hybrid hydrogel 2040, that is 2% arginate with 4% CNC, displayed a highly porous microstructure with a uniform pore size of 20 micrometer. Thus, the addition of CNC in arginate network improved the pore size and porosity, providing an ideal environment for cell activity. Rheological tests were done on the bioink. We compared the pure arginate in black and the hybrid bioink in red and found significant differences between them. The hybrid bioinks exhibited strong shear thinning behaviors, which is contributed to the hydrogen bonding between arginate and CNCs. On the other hand, increasing arginate concentration from 2% to 6%, the viscosity increased over the whole shear rate range, but do not imply strong shear thinning behavior. With same polymer concentration, their viscosity varies a lot at the low shear rates. For instance, the viscosity of 6% arginate is constant at low shear rates at a magnitude lower than the bioink 2040. So it suggests the hybrid solution enhances the printability and the fidelity. In the shear thin region, the flow curve conforms to the power law model. Taking 2040 as an example, the slope is negative 0.77. An estimated shear rate at the nozzle wall while printing can be obtained based on the flow rate, the nozzle radius, and the value n. We conclude the applied shear rate at the nozzle wall is around 300, and the viscosity is 0.5 pascal/second. This value is roughly 3 orders of magnitude lower than those at low shear rates, enabling the bioink being extruded through a 100 micrometer inner diameter nozzle rated with no clogging. In pure arginate, showing in black and blue, the elastic modulus is smaller than the viscous modulus, indicating that pure arginate, even at 6%, is liquid-like and not suitable for 3D printing. However, the elastic modulus is higher than the viscous modulus of the hybrid bioink, indicating more gel-like behavior. No crossover of G prime and double prime at low frequencies means that the bioink possesses a permanent rigid gel network. To evaluate the printability of the ink, 5 formulations were studied. We designed a lever-lobe mimetic honeycomb structure. Pure arginate with a low shear viscosity gave a poor fidelity while printing. With the increasing concentration of the added CNCs, the geometry accords with the input design. The contract printed by 2040 showed low deformation and relatively high accuracy. Therefore, cell suspension was added to the 2040 bioink for cellular bioprinting and studied its biocompatibility. Fibroblasts and hepatoma cells were encapsulated in 2040 and printed in the honeycomb and middle cavities separately. No significant difference in cell viability was observed in the molded and the bioprinted constructs, indicating that the bioprinting process is cell compatible. However, after 3 days, cell viability of both cell lines decreased, which may arise from the lack of cell binding sites in the hydrogel. It limits cell adhesion, viability, and proliferation, which was also confirmed by the fluorescent images. To circumvent such issue, one potential solution is incorporating polymers containing cell binding sites, such as GERMA, into the system. There is an ever-growing amount of evidence reported in research literature that GERMA is effective in promoting the cell attachment due to its RGD tripeptide sequences, which are the major integrin binding domains present within extracellular matrix. So we developed our second version bioink that is 1% arginate, 3% CNC, and 5% GERMA, and the pure 4% GERMA. We studied the rheology as well. GERMA's viscosity is around 0.1 pascal/second and varies little over the whole shear rate range. The incorporation of CNC and arginate into GERMA solution significantly altered the intermolecular interactions, leading to a strong shear thinning property with a curved slope of negative 0.85. The viscosity is close to 1000 at 0.1 shear rate, which is 1 magnitude higher than the bioink 2040, indicating 135 ACG's superiority for bioprinting. In 4% GERMA, the viscous modulus was higher than the elastic modulus at low frequencies and only around 1 pascal, indicating the pure GERMA was more liquid-like at low frequencies and not suitable for bioprinting. Thus, we deposited GERMA in middle cavities, which was supported by the honeycomb structure. The elastic modulus of 135 ACG were higher than the viscous modulus and over 100 pascal, meaning it's more solid-like and can produce scaffolds with good structure fidelity. By using 135 ACG, structures with favorable fidelity up to a height of 1.8 millimeter is obtained, but spreading and collapsing occurred later. As mentioned previously, mechanical strength and the degradation profile are essential in developing bioinks, thus we did some tests on it. The compressive modulus of 4% GERMA hydrogels was around 4 kPa, within the range of the stiffness of a healthy liver, meaning 4% GERMA provides a soft and stable environment for HepG2 cells. Compared to the GERMA hydrogel, the hybrid hydrogels were much stiffer, over 10 kPa. Upon cell suspension in both bioinks, the modulus reduced due to the softer cells and the material voice. Interestingly, the compressive modular of both a cellular and the cellular 135 ACG hydrogens increased on day 14, which can be attributed to the strengthening of arginine network by calcium ions in the cell medium. Bicellular 3D construct with direct contact and non-contact interaction between HepG2 and the supporting fibroblast cells were fabricated to study the effect of the co-culturing. In the direct contact system, fibroblasts and the HepG2 cells were mixed in germa filling the middle cavities. HepG2 cells spheroids were formed and the fibroblasts elongated and spread over time. Interestingly, fibroblasts protrude from the soft germa matrix to the stiff 135 ACG hydrogens due to the durotaxis, and they align parallel along the boundary between the two different materials. In the non-contact system, fibroblasts were printed in the outer honeycomb and HepG2 cells were deposited in the inner cavities. Fibroblasts were found to proliferate and elongate in 135 ACG hydrogens and align along the boundary as well. Interestingly, the two types of cells migrated towards each other over time, and a direct intercellular contact at the boundary occurred as shown in the blue circle. Besides the study on cell morphology and proliferation, albumin secretion, a liver-specific marker, was measured to assess HepG2 function in 2D, 3D monocellular, and 3D bicellular co-culture systems. Compared to 2D system, albumin secretion hiked up dramatically in all 3D cultures, indicating 3D germa ECM promoted per cell albumin secretion significantly. From day 7 to day 14, we also observed that higher amount of albumin was produced in the co-culturing system, which could be explained by the presence of fibroblasts. Compare the direct and the indirect intercellular contact systems. There was no significant difference, suggesting that the physical contact of the dual cell lines might not be necessary to influence the hepatocyte function. Rather, the fibroblast secreted factors matter. Besides the work on bioprinting liver lobule mimetic construct, we also work on fabricating a tumor model. The current exacerbation models may influence endocrinological factors vital to cancer cell viability. Hence, there is a pressing need to fabricate an exacerbation model consisting of human vascular endothelium that function as a barrier for the traversing of circulating tumor cells to better mimic the blood vessel microenvironment. In this work, we prepared a much stiffer bioink consisting of higher concentration of arginate germa and CNCs. It possesses a superior shear thinning with a slope of negative 0.94. Zigzag, change, and V-line patterns were printed by bioink with the same polymer concentrations as shown in the right figures. It's obvious that the hybrid bioink 246 gave high shape fidelity, and the in situ cross-linking was employed to further reduce spreading, bending, and rounding of the printed structures. Therefore, the bioink 246 was used for tumor model printing. We designed a colorectal cancer exacerbation tumor model with two distinct regions called change and V-line to assess the capability of our novel bioink 246. The change region was devised to mimic a blood vessel cut in half, and the V-line region was to mimic the intestinal V-line. To achieve an appropriate tumor model for investigating exacerbation, we not only should have a monolayer of endothelial cells even on top of the V-line, but also need to be able to precisely deposit cells in a well-defined pattern. However, from the fluorescent images, there were no cells attached at the top of the V-line. After seeding EAHY 926 cells on the substrate, despite treating the print model with polyair lysine. Therefore, we use cell-laden bioinks prepared by 135 ACG. to print a monolayer of endothelial cells and the clusters of cancer cells at a specified location on top of the base scaffold, which was printed by BioInk 246, as shown in this schematic. From the fluorescent images, a monolayer of EAHY926 cells formed on top of the villi and the change structures. HCT116 cells, as shown in the reddish color, were precisely deposited at different places, such as inside the channel. These images also confirm the accuracy of our bioprinting method. To conclude, we studied the series of hybrid BioInk systems incorporating nanomaterials, CNC, and the biopolymers for the high resolution and high-speed printing of 3D tissue constructs via microextrusion. We found that the CNC with proven biocompatibility played a vital role in improving BioInk's rheological and mechanical properties. Two structures with well-defined biomimetic geometries were successfully printed, including bicellular liver lobule mimicking constructs and layered colorectal tumor models. Cell viability function, cell-to-cell interactions, and cell-to-ECM interactions in the printed 3D structures were studied as well. Overall, our studies offer a promising route to greatly enhance BioInk formulations for printing complex architectures with multiple ECM components and cell types in sufficient resolution to recapitulate biological functions. That's it. Thank you all for listening.
Okay, so that was interesting. We have the next talk from Yuna Love. Do we have her today? Do we have him today? Okay, let me check if I have the video. Yeah, so I have the video for this particular talk, and if Dr. Yuna Love is not here, I can straight away share the video. And this is about image-based non-segmentation finite element method for mechanical characterization of composite materials with fine inclusions. Quickly share this.
Welcome to my presentation. First, let me introduce myself. My name is Yunhua Luo. I am a professor at the Department of Mechanical Engineering in the University of Manitoba, Canada. In this presentation, I will report our recent progress in the development of non-segmentation image-based finite element modeling. Since image-based finite element modeling has been widely used in the characterization of composites and in biomedical engineering, why there is a need to develop the so-called non-segmentation image-based finite element modeling. To answer this question, I will first review the deficiencies of conventional image-based finite element modeling. Following that, I will present the main idea of non-segmentation image-based finite element modeling and the results of a convergence and validation study. I will conclude my presentation with the main findings. So basically, two types of finite element models can be constructed from material images. The first one is focus-based models. That is, finite elements are directly generated from image focuses. These kind of models are effective for capturing material heterogeneity and is mainly used by biomedical researchers for the assessment of bone strength and fracture risk. But this method is computationally very expensive. The other type of finite models are geometry-based models. So a geometrical model of the material microstructure is required for this approach, which is constructed by segmentation of phase materials. Finite elements are aligned with the interface of phase materials. Each element is allowed to have only one phase material. There are a number of deficiencies for this approach. It often fails to generate a finite mesh, and then the quality of the finite mesh is often a concern, and it also has difficulty to achieve high volume fraction of inclusions. To eliminate the deficiencies in the previous two types of finite models, we developed a so-called non-segmentation image-based finite modeling approach. In this approach, composite microstructures is represented as digital images. Segmentation of phase materials is not required. This is why it's called a non-segmentation modeling approach. The finite element mesh is independent of the microstructure. Element is allowed to have more than one phase material. The key step in this approach is to calculate effective material properties in each element. Calculate element effective properties. Volume fractions of phase materials in the element are required. To calculate volume fractions of phase materials in an element, we first find out all the focus cells located in the element and then identify their material types. Volume fractions of the phase materials calculate is the ratio of the focus cells of the material types. With the determined volume fractions of phase materials in an element, now we are able to calculate element effective properties. Theoretically, all formulas developed from micromechanics of particulate composites can be applied here. We implemented 4 of them. Their Riemann-Summer equation, rule of mixture, inverse rule of mixture, and Mori-Tanaka formula. It was found out that Riemann-Summer integration is equivalent to the rule of mixture. We studied the convergence behavior of the non-segmentation image-based finite modeling and find out that the process of convergence is independent of the method that is used to calculate element effective properties. The results shown in the following figure are produced by using Mori-Tanaka method. It can be seen that the convergence process is steady and the convergence rate is high. We used an experiment case for the validation. The composites are a series of glass microsphere filled polyester with different volume fractions of polyester in the glass. The Young's modulus and Poisson ratio of the composites were measured by experiments, And the phase material properties are available for finite element modeling. A cubic representative volume element of the composites was used in finite element modeling. Young's modulus and the potency ratio were predicted by non-segmentation image-based finite element modeling and voxel-based finite element modeling. The voxel-based finite element modeling is accurate to capture material heterogeneity. Some of the validation results are shown here. In this figure, showing the results related to Young's modulus, the solid black circles represent experiment data. The red line is the result of voxel-based finite element modeling, and the blue dashed line is the rule of mixture, and the green line corresponds to Mori-Tanaka method, and the black dashed line is the inverse rule of mixture. So from this figure, it can be seen that the inverse rule of mixture has the best agreement with the experiment data. This figure shows the results related to Poisson's ratio, and from the figure it can be seen Mori-Tanaka method has better agreement with the experiment data than the other two methods. So from the results, it can be observed that the accuracy of non-segmentation image-based finite element modeling is greatly affected by the method to calculate element effective properties. None of the four methods has good agreement with both of the experiment data and the results of voxel-based finite element modeling. Therefore, further efforts should be devoted to find out or develop a more effective method for the calculation of element effective properties. Thank you for watching my presentation. If you have any question about my research and the presentation, please send me an email. Thanks.
Okay, all right. So after this interesting presentation, the video that we saw, do we now have Dr. Fatma Saq with us? Dr. Fatma Saq? Okay, if not, I can check if we have a video. Okay, unfortunately, I don't have a video. And we can go to the next presentation, and that's from Dr. Agnieszka Szovanik. Do we have Dr. Szovanik here? Okay. So I have the video, and we can see this video about analysis of the adhesive properties and microstructure of epoxy resin coatings modified with waste limestone powder. So I quickly share this video. Okay, I'm sorry, we don't have the video, but we just have the PPT. But I think it will be interesting to have some email conversations with the authors to understand more about their work. And because we don't have any video, and now do we have author with us? We can move on. We can move to the next presentation. Do we have Dr. Esnalasamy with us? Okay,
hi,
yeah.
sir. I think for the speaker number 8, the video is come with the sound, so we can like the PPT comes with the sound, so we can play it.
Okay, let me check that. Thank you for letting me know. Okay. Yes, that's right.
Good afternoon, everyone. My name is Agnieszka Chowaniec, and I am a PhD student at the Wrocław University of Science and Technology in Poland. In our presentation, I would like to present the analysis of the adhesive properties and microstructure of epoxy resin coatings modified with waste limestone powder. In the introduction, I will discuss the basic information about epoxy resin floors and the research motivations. Then I will present the materials and method descriptions, results and conclusions. Beginning with the introduction, it is worth to mention that the typical floor consists of a substrate and a coating. Industrial coatings are increasingly made of epoxy resin. The epoxy resin coating very often consists of 3 layers: a bonding agent, a base layer, and a finishing layer. All 3 layers consist of 2 elements, an epoxy resin and a hardener. Waste limestone powder is a waste material from mechanical fragmentation of rocks. In our study, waste limestone powder was added to the base layer. The main disadvantage of the epoxy resin is its harmfulness to the environment. Compounds contained in epoxy resins are toxic to aquatic life, causes skin and serious eye irritation, may cause an allergic skin reaction, and are harmful in inhaled. The epoxy resins are very expensive and cost over 100 times more than cement. Therefore, there is a need to find a solution to reduce the total mass of epoxy resin used to make the coatings without deteriorating the durability of these coatings. Considering the durability of the epoxy resin coatings, it is required that these resins are characterized by a high pool of strength. As you can see in the picture, the pool of strength of coating is the value of strength when peeling the coating from the substrate. For the epoxy resin coating, the minimum average value of pool of strength is 1.5 megapascals. The main goal of the research is to find an amount of waste limestone powder that at least not deteriorate the pool of strength of the epoxy resin coating. The aim of the research is to reduce the total mass of harmful epoxy resin needed to make the coating by using a waste limestone powder as filler. Waste limestone powder is not harmful to the environment. Moving to materials and method description. In the research, we use an epoxy resin coating consisting of 2 components, A and B, whereby component A contained an epoxy resin and component B was hardener. We use waste limestone powder as an filler. The used waste limestone powder had all grains with a diameter below 25 micrometers and had a mass composed almost entirely of calcium carbonate. In our research, we prepared a concrete substrate and divided it into 2 areas with different methods of substrate surface treatment. We grinded half of the surface of the substrate mechanically to obtain a ground surface. The other half of the surface was a raw surface. We separated squares of both types of surface. Before applying the coating, we've examined the morphology of the concrete surface using a 3D laser scanner under each measuring point where pull-off tests will be carried out. Then we made the coating. We covered control squares with epoxy resin without the addition of powder, and the remaining square with epoxy resin with a gradually increasing content of the waste limestone powder. We added the waste limestone powder to the base layer in an amount from 7 to 29%. Going to the test results. Figure 7 shows a comparison of the exemplary results of the surface morphology examination of both types of substrate surface using a 3D laser scanner. The raw surface was more varied between the measurement points. For the raw surface, there was greater differences between the highest and lowest points compared to the ground surface. For the ground surface, the examined areas looks almost the same as in Figure 7c. We took the measurements of the pull-off strength at 3 points for each square on two types of surface. As shown in Figure 8, ABC, the standard distinguishes several possible modes of spaceman failure. We have determined the type of failure for each measuring point. Examples are shown in Figure 8D. For the raw surface, failure for the thin layer of cementitious materials was observed at 4 points. In the remaining points, the failure occurred at a greater depth in the concrete. In Figure 9, we presented the obtained values in the form of a graph of the relation between the content of the waste limestone powder and the pull-off strength of coating. The contour samples of both types of surface obtained almost the same results, about 2.9 megapascal. The pull-off strength results for all samples are above the normative minimum pull-off strength value. All average pull-off strength values are between 2.3 and 3.2 megapascals, which shows that the addition of waste limestone powder generally did not deteriorate the pull-off strength of the epoxy resin coating. We evaluated the microstructure of the samples using a scanning electron microscopy. Figure 10 shows the cross-section of the sample's height at 100 magnifications. Analyzing the obtained data in ImageAid and Mathematica, we created images of segmented pore, which are shown in the graph as black pixels. Then we constructed the porosity plots shown in Figure 11. In this graph, it can be seen that the R0 sample from the raw surface is characterized by a slightly higher porosity of the subsurface layer of the substrate compared to the sample from the ground surface. Finishing with the conclusions. The tests showed that the level of surface roughness is lesser for the ground surface compared to the raw surface. For the ground surface, the failure during the pull-off strength test always occurred in the concrete, so the pull-off strength value depended mainly on the tensile strength of the concrete. For the raw surface, in some of the measuring points of the pull-off test, the failure occurred in the thin concrete subsurface layer. This was due to the lack of grinding of the surface and the lack of removal of weaker layer of the concrete subsurface. For the raw surface, slightly lower pull-off strength results were obtained compared to the ground surface. Most of the pull-off strength results for the coating with limestone powder were within the standard deviation of the results for the reference samples. Based on the porosity graphs along the height of the samples, it was noticed a slightly higher porosity of the subsurface layer of the substrate for the raw surface compared to the ground surface. In conclusion, it is recommended to grind the surface of the concrete substrate before applying the epoxy resin coating. The addition of waste limestone powder in the amount of 7% to 29% generally does not deteriorate pull-off strength of epoxy resin coating. So, the waste limestone powder can be used as filler for epoxy resin coating. This will reduce the total mass of harmful epoxy resin needed to make the coating. Thank you very much for your attention.
All right, so, okay. Now I see that we have Dr. Fatma Sarf with us, so we can go one presentation up and listen from her. Dr. Fatma Sarf, can we hear that from you?
I can hear you.
Okay,
Can you hear me?
do you hear me?
Yes, I can.
Okay, so, okay, we can hear from Dr. Fatma Sarf, and she'll be talking about a correlation between oxygen vacancies and elemental analysis in single and binary transition metal oxide structures. So Dr. Fatma Sarf, it's over to you.
Can you see my PC screen right now?
Yeah, can you please go to the presentation mode?
Okay. Hi everyone. It is Fatma Sar from Çanakkale 18 Mart University in Turkey. Can you hear me?
Yeah, can you please play the slideshow? Okay. Or maybe if you have this Windows computer, you can just press F5.
Right now, can you see?
Okay, we don't see the slideshow, but okay, anyways, we can get started. No problem.
Okay. I don't know what is the exact reason for the unseen the screen. Okay.
No problem.
I would like to share our work with you today. My name is Fatma Sar from Çanakkale 18 Mart University in Turkey. This study's title is A Correlation Between Oxygen Vacancies and Elemental Analysis in Single Binary Transition Metal Oxide. First, this presentation aims to show a relationship between elemental analysis and oxygen vacancy tests for metal oxide nanoparticles and thin films. Although this is not a numerical or direct correlation, the results appear to be significant. I would like to make a simple introduction, if you let me, in relation to transition metal oxides, elemental analysis, and oxygen vacancies. Okay. Functional properties of metal oxides are strongly dependent on oxide crystal structure, composition, defects, doping, and blah, blah, which govern their optical, electrical, chemical, and mechanical properties. The band gap and electronic structure of oxides can be controlled and tailored by the size and dimension, resulting in a wide range of potential applications. One of the motivating classes of material comprises transition metal oxides that display an assortment of properties. The nature of bonding present among metal and oxygen can be fluctuating from partially ionic to extremely covalent or metallic. Owing to process outer the electron nature, the properties of transition metal oxides are unusual. Transition metal oxides can be documented as the class of oxides that comprises of cation which has incompletely or partially filled the shell. This nature is due to their marvelous feature as they are motivating and scientifically supreme category of versatile materials. This class contains a wide range of color, magnetic, optical, and electrical properties, along with most researcher classes to progress their understanding of nature. In figure 1, we can see that the scope of research in as a transition metal oxides in oxide articles, and this can be also generalized.
Dr. Fatma, I'm sorry to bother you. I don't see the slides moving. Is this the case with everyone?
Sorry?
We don't see the slides moving.
Yeah, we don't see the slides moving. Okay, I think she got cut off. We can just wait again. Yeah.
Can you see that?
Yeah, we don't see these slides moving. So what we see here is this, the first or second slide that's about transition metal oxides. Okay.
I don't know what is the exact reason. Right now, your screen sharing is. Can you see that?
Yes. Yes. Now we are on the next slide, on figure 2. That's right.
Okay. Can I start again?
You may continue, no problem. You can just continue from figure number, the next slide.
Okay.
Yeah.
Figure 2 shows transition metal oxides and other components used in catalyst studies. And in short, these materials can be expanded in binary and other forms. And in figure 3, you can see that transition metals in the periodic table, such as vanadium, titanium, zinc, copper, nickel, and other elements. Okay. So elemental analysis technology is widely performed to determine the composition of materials. Elemental analysis can be both qualitative, that means determining what elements are present, and quantitative is meaning that determining how much of each are present. In figure 3 shows the general meaning of the EDX analysis of transition metal oxides. In 2016, Comaria and their colleges presented a study. They give in this analysis, it is confirmed the presence of zinc and oxygen elements in this structure. So when we apply EDX on the material, although we know the elements in it proportionally, but stoichiometric values may be low or erroneous due to excess of oxygen. Okay. Another side, we can see that about what can be said about the photoluminescence analysis. When the photoluminescence spectra of the transition metal oxides are examined, different levels of defects are noticeable. In transition metal oxides, various types of defects, including lattice defects, vacancies, and unsaturated coordination states, could act as active state in necessary application reactions. What is the mean of defects? Defects are deviations from the periodic structure in the crystal. The destruction of the crystal structure will lead to new properties of the electronic and other structures, which is different from that in the perfect crystal. At the same time, the defects in crystal will also cause the disruption of electricity with the trap energy levels they replace it, thereby increase the binding energy of metal oxides and metal atoms. Therefore, the defects in applications will tune the reaction surface and between surface and interface properties. So surface defects play a stronger role in the controlling transition metal oxide properties. It is also critically important to understand defects in transition metal oxides, doped with different type metal ions, either purposefully for achieving a certain functionally or through accidental doping during the growth process. It is important to understand the relative dominance of carriers introduced by the doping over native defects. In donor situation, the generation of free electrons in zinc oxide in figure 5, we can see that zinc oxide band gap and energy levels of native defects like as donor or acceptor in zinc oxide structure. We are interested to oxygen vacancies in this structure. We can see that all the octahedral states are empty and there are plant states for zinc oxide to accommodate intrinsic. It means that interstitial defects and extrinsic dopants. As a result, defect relative emission in zinc oxide exhibits itself as a broad structured band spreading from blue to red spectral regions. Similar situations are observed in tungsten oxide and nickel oxide structures. In this study, we interested to these three types: zinc oxide, nickel oxide, and tungsten oxide structures. Okay, In this study, we will discuss simple, cheap, and vacuum-free systems, since the main factor determining the relationship between EDX and PI for oxygen is heterogeneous, it means that homogeneous growth process, which perhaps the most convenient to observe, and we often work in this direction. To synthesize nanoparticles and thin films, respectively, co-precipitation and chemical bed deposition methods were used. To investigate PI spectrum in the range 350 and 700 nanometer range, samples were excited at appropriate wavelengths. Okay, first material is precipitated zinc-doped zinc oxide nanoparticles. X-ray diffraction, FCM images, EDX analysis, and PL spectrum of this material were shown in this slide. Okay, we can see that zinc oxide nanoparticles have hexagonal virtuous structure and high crystallized, and 101 is preferential orientation for all the films, and by the increasing zinc concentration in the structure, the crystal is improved, and by the increasing zinc concentration, agglomerative forms and spherical forms were changed as nanorod forms. And when we investigated the EDX analysis of this structure, oxygen concentration is decreases with the increasing zinc concentration, and similar situation is observed in PL spectra. We can see that green emission in the PL spectrum, and by the increasing zinc concentration, oxygen vacancy related peaks were decreases by the increasing zinc concentration. Okay, this is the first material in this study, and other is chemical bed deposition. Again, zinc doped.
Can you please wrap it up in another 1 minute? Thank you.
Okay. We can see that nanoflower and nanoflower nanorod mixing structures and oxygen vacancy defects in the PL spectrum. And another study is including nickel doped tungsten oxide thin films, and we see again the tungsten concentration increases with the increasing nickel concentration, and oxygen is decreasing by the increasing tungsten concentration. And another study is including precipitated nickel oxide nanoparticles, and from our previous studies about the nickel oxide tin oxide nanoparticles mixing. And we also see again oxygen concentration is very high in this system. This is about the heterogeneous film or nanoparticle growth in these systems. And finally, our conclusions in this study: simple synthesized oxide-based thin films and nanoparticles were investigated. Both nanoparticle and thin film transition metal oxide samples show high polycrystalline and no impurity-based peak is detected. Different type surface forms such as nanorod, nanoflower, nanoprism like this are observed with agglomerative film forms, which is indicating heterogeneous growth process. EDX analysis shows that oxygen and metal peaks have been detected and no impurity peaks are observed. However, solution-based peaks were observed, which is probably main reason for agglomerative forms. With agglomerative forms as seen in FCM images have an impact on the increase of oxygen elemental ratio up to 50% and decreasing low metal elemental ratio causes heterogeneous growth, and increasing hydroxyl metal forms may be affected. And finally, local point defects, especially oxygen vacancies, increases with agglomerative forms, including samples. Therefore, high oxygen elemental ratio is shown in elemental analysis of the samples. Thank you for listening.
Okay, thank you very much. So for the sake of time, we can take questions later, just in case we have time. So Dr. Fatma, thank you for your presentation. We can move to the next presentation now. And if we could stop sharing your presentation and just move to the next presentation. Next is from Dr. S. Nalasamy. Do we have Dr. Nalasamy in the room today? Okay, if not, I have his video with me and I will share that. And it's about, his talk is about design and analysis of epoxy granite reinforced with steel vertical machine center spindle housing. So I'll quickly share this video. Okay.
Very good morning to one and all. I am Professor Dr. Nallasamy, Professor and Dean of Mechanical Engineering from Dr. MGR Education and Research Institute. It's one of the autonomous deemed to be university in Chennai, Tamil Nadu, India. My research topic is design and analysis of epoxy granite reinforced with steel vertical machining center spindle housing. The aim of my research is to design the spindle housing made of epoxy granite reinforced with steel for a vertical machining center as a substitute for the currently used cast iron housing, with the aim of improving the dynamic performance and to increase the damping potential of the structure while retaining the stiffness properties. The methodology which is used in this research is a steel reinforced epoxy granite structure could be proposed for VMC spindle housing, and moreover the proposed model could be analyzed for the static structure considerations. in current industry scenario, the industries are nowadays focusing more on achieving high quality products only. Generally, machine tool structures are subjected to continuous distortion and unwanted vibrations during machining process. In order to resist these effects, the structures should have better dynamic properties. Hence, cast iron has been used as structural material for structures of machine tools. In case of high-speed machining, high damping properties are required. The lack of desired dynamic properties results in dimensional inaccuracies in the components. Machining centers are one of the solutions which employ metal removing process to achieve high productivity and high quality. High damping properties and stiffness of the machine tools structures greatly influence the quality of the products. In machine tool, most of the components are made of cast iron as it possesses better dynamic response compared to other materials. So recently we are using only the cast iron for machine tool structures. So we are planning to change the cast iron into some other reinforced material. So the design of spindle housing in machine tool structures, all the structures including base, column, etc. encounter both bending and torsional loads. The base and column experiences load in a distributed manner, but the spindle housing sustains a point load at the tool tip. Also, the torsional load experienced by the spindle housing is higher than the other structures of the machine tool. Hence, the spindle housing are generally designed with higher stiffness. In this research work, the newly proposed composite spindle housing and cast iron spindle housing are analyzed for common force and boundary conditions to get the better results and to found which one is the best option to go for the structural materials. The levels of forces and periphery, we have been analyzed the structure of the structure by using ANSYS, the software of ANSYS R18. Based on the figure which is shown in the slide, the ball screw mount at the back side of the spindle housing is considered as the fixed support. The surfaces on which the linear motion pad are to be mounted are considered directional supports along the X and Y directions. The cutting force for worst case machining conditions is estimated and applied at the tool tip. The magnitudes of the components of forces in each force configuration of machining, such as X, Y axis milling, Z axis for drilling, are listed, and the results are tabulated in the following table. Since the component, the forces are X, Y and Z, where the magnitude which has been observed in x-axis feet, the magnitude is 2350 and y-axis is 850 and z-axis 1300. Similarly, for y-axis feed, component x force is 850 and y force is 2350 and z force is 1300. As far as z-axis speed is concerned, the x component comes under 0 and y component comes under 0 and the z component forces comes under 2500. The cast iron spindle housing, normally we have taken the spindle housing of 6 different design configurations of DC1 to DC6 made of cast iron have been considered. These 6 configurations are made with the consideration of manufacturing flexibility through casting process. In design configuration 1, the across ribs inside the spindle housing are made referring to the existing cast iron spindle housing. Normally, the circular ribs along vertical axis are to be introduced to reduce stress concentration in the spindle housing. In case of design consideration 2, is similar to DC1 but added with features like fillets, chamfers and circular structures at the joints for stress reduction. So here all the 6 cast iron structures which has been created are shown in the figure. So the deformation for cast iron spindle housing has been calculated. That should be that has been given in the table following table. The DC1 total deformation for DC1 is 41 and DC2 is 14, DC3 is 14, DC4 is 65, DC5 is 77 and the total deformation is for DC6 is 51 micrometer. In DC3, the front end of the spindle housing is designed with curved edges as the sharp edges experience higher stress. DC4, DC5 and DC6 are provided with the slotted side plate structures and horizontal ribs for improving the stiffness. The 6 configurations of cast iron spindle housing are analyzed for structural loads and the results are tabulated. From the tabulated results, it can be seen that the minimum deformation achieved in 14 microns and this has been taken as the benchmark value, and the permissible deformation in the composite spindle housing is considered to be 14 microns for all the deformations. Composite structure of epoxy granite steel housing. This is our proposed composite structure. In the composite epoxy granite steel spindle housing, the steel reinforcing structure placed inside epoxy granite housing should be designed in such a way that it withstands all the loads acting on the housing without the deformation exceeding the set limit. The epoxy granite over the steel reinforcement would provide damping to the variations during machining. To obtain the optimized steel reinforced structure topology, optimization is used. The topology optimization of steel reinforcement for spindle housing. To develop a block structure is analyzed for static performance, and then using the topology optimization tool, the locations where additional material is required is highlighted. Similarly, the various structures have been analyzed, and we are going for steel reinforcement structure design also. The deformation results of initial configuration of reinforcement due to the cutting force are listed in table, and it can be seen that the deformation is very much higher than the permissible value. That the deformation value for DC for the different ratios and desired effect of reinforcement are given in the table. Whereas the DC7 is made with I section beam at the center along with the y-axis. The support rods are added in an inclined manner between the corner of support plate and I-beam at a position close to spindle. The description of the reinforcement desired effect on the structure due to reinforcement and influence of the structure on the deformation and the directional and the resultant deformations of the D7 to D12 are tabulated. These are the results of deformation for D7 to D12, whereas from the results we are going to shoot out the appropriate design. In case of composite epoxy granite steel structure, the steel reinforcement will be embedded inside the epoxy granite mold such that steel provides stiffness and the epoxy granite provides damping to the vibrations. The configurations of steel reinforcement with exhibited better structural performance are placed inside the epoxy granite housing structure with 25 mm wall thickness, and the composite structure is analyzed for the static structural conditions. The analyzed structure of the epoxy granite with steel configurations is shown in the following shown in the next figure, and the results, the machining configuration results are given in the table. The composites spindle housing design for DC13 has been analyzed for the deformation, and the results are given in the table. The results of the structural analysis shows that the maximum deformation of the steel reinforced epoxy granite spindle housing is found to be less than 10 microns. When compared with the cast iron housing, the values of the deformation are much lower in our proposed steel reinforced epoxy granite spindle housing. See, these are the main conclusions based on our research and analysis. The initial reinforcement design of DC1 has been arrived at from the topology optimization. The addition of reinforcement to the initial steel structure of DC1 has been reduced deformation from 230 microns to 6 microns in the improved steel reinforcement structure of DC13. The reinforcement with I section in the epoxy granite is found to resist deformation than other reinforcements. The improved steel reinforced epoxy granite spindle housing design possesses better stiffness compared to the cast iron spindle housing. Hence, the improved I section steel reinforcement epoxy granite spindle housing is more suitable than the cast iron spindle housing. Hence, we can suggest instead of cast iron spindle housing, better we can go for the improved I section steel reinforcement epoxy granite spindle with steel, which is having more stiffness and more mechanical properties, and this can be suggested for the future references. Thank you one and all.
Right. So we always contact the authors to discuss more about their works. Now we can go to the next presentation. Do we have Dr. Hendrik Paradise with us today in the room? Okay, if not, then I have their video and I can quickly share that video with you all. Okay, so this presentation is about non-equilibrium lipid A phosphate phases against bacterial and antiviral infections. I will quickly share the screen. Okay. There we go.
This talk on non-equilibrium lipid A phosphate phases against bacterial and viral infection encompasses dual lipid A phosphate phases, which can be used in therapy and including viral therapy as well as vaccines for carrier of the messenger RNA. Lipid A diphosphate are the abundant components of bacterial lipopolysaccharides and are found on the surface of gram-negative bacteria, and it is the major component of the outer leaflet of the outer membrane of these bacteria. Recent investigations have shown a variation in microbiome LPS immunogenicity, contributing significantly to autoimmunity. Hence, Figure 2 depicts a model proposed by Xavier and Podolsky in 2000 with all the comments on bacteria of pathogenic bacteria and pathogenic bacteria and their interaction with their clinical parameters, which we will show later on in another slide. The chemical structure of lipid A phosphate from non-toxic lipid A consists of 2 beta 1.6 linked D-glucose amine units with polar phosphate groups at 1 and 4 prime positions. The 2 and 2 prime amino position and the 3 and 4 hydroxyl group are esterified with hydroxy fatty acids. The commensal microbiota affects the mucosal and systematic immunity, playing a potential role for microbial keystone species in autoimmunity. The biological activities result from the active known as lipid idiphosphate or also endotoxin. This slide shows the changes of clinical parameters during administration of lipid idiphosphate vaccines to patients which suffer from chronic sinusitis for a period of 4 weeks. The various levels of the stimulation of the cellular and the humoral immunological defenses are shown as outlined and are the same one as shown in the slide of figure 2. This figure 5 and figure 6 shows various colloidal lipid A diphosphate crystals and their appearances, and the one on the left side, down on the left side, shows the indexes of the dodecahedral crystals, whereas the other ones, electron microscopy pictures of lipid A diphosphate of the various forms and approximates of the lipid A diphosphate. This is more or less the key in the understanding of the phases of the different self-assembly charged lipid A diphosphate at 291 Kelvin as a function of particle number density and ionic strength. In A, one sees the ordered crystal phases which appeared after considerable reduction of ionic strength, with a larger Debye length and NaCl due to a stabilized electrostatic repulsion between the various self-assembled lipid A diphosphate clusters shown in figure 5. Figure 7 shows colloidal single crystal composed of identical or non-identical lipid A diphosphate molecules or approximates in icosahedral symmetry and arranged according to McKay, published in Acta Crystallographica 1962. A layer packing can be arranged which correspond to a local Penrose isomorphism, which includes a decomposition and includes an addition of rhombohedral above and below layer packing. On the encircled red one box, it shows single crystal of 0.05 millimeter of lipid A diphosphate, whereas the other one is just a packing of icosahedral faces according to Penrose. This figure shows small angle X-ray scattering profiles versus scattering vector Q for the SEC type colloidal crystal of lipid A diphosphate cluster with A 57 nanometers, and for the derivative composed of 1D and 1C shown in figure 1. For a unit cell of A of 45 nanometers and 2 different ends, this will mean different subunits at a concentration of salt of 5.23 micromolar sodium hydroxide. With these results, we can go to the composing the assembly to a tetrahedral close packing of a face cubic lattice FD3N and simple fluidic lattice PM3N, and where the tetrahedral and closed packed lipid A diphosphate and lipid A monophosphate structure for 2 cubic crystalline phases using Wegener light cells. For both structures and aqueous bilayer compartmentization, the hydrophobic portion of the lipid A phosphate is arranged in tetrahedral in networks. The liquid is a combination of a pentagonal phase center, the simple cubic center dodecahedron in blue, with a 14-phase polyhedra in green on a M3N, and with a 16-phase polyhedra green in the phase center cubic lattice. Again, the line is a 2D lattice concept for lipid A diphosphate and their complexes. This figure shows typical classical conglomerate or web lattices declined by the interface triangle, where each mode is surrounded by 4 neighboring modes. And in B, a Fourier transform image of A, and on the other one, in F, is a schematic of the Kagome lattice indicating the chirality of lipid A diphosphate, clockwise rotation 6 P3 and M1 with CX by L. Quasi-crystalline structures exhibit a non-crystallographic packing of non-identical lipid A diphosphate spheres. The spatial packing was in either a cubo-octahedron or an icosahedron. It was noted that the observed 3.3.4.3.4 tiling was a crystalline analog of the icosahedral quasicrystal. The tiling pattern of the triangles and 3 and squares and 4 possess a P4GM plane group. Another coded lipid A diphosphate approximation showed an 8:3 ratio with 6-fold symmetry and plane group P6MM. Both endodecanate phases revealed a N3 and 4 ratio of approximately 2.34. Because of bond orientation order, the direction of domains was classified into 3 orientation for the 3.3.4.3.41 tiling, but only 2 for the 8/3 approximates. The linear Poisson strain was quite small, only 0.02, and much slower than the phonon strain. This could be the same reasoning with different subunits. This phase diagram encompasses all phases of lipid A diphosphate as a function of kBt over the particle number density, and with K is the Hückel length. And the theory is in accord with the melting and with the forming of crystals depending on the counter-ion concentration, and the second term in the excess of the electrolyte is just calculated according to the linear multiples in the scale theory, and according to Robbins, Kramer, and Grest, as well as from Mayer and Frankel. This is a summary of the experimental obtained different phases who have been characterized by electron microscopy, X-ray diffraction, neutron diffraction. The different behavior of the self-assembled coded or uncoded lipid A phosphate interacts with the lipid rafts in the membrane process, including protein sorting, vesicle transport, viral entry, and exit from cells and signaling. The observed executive phase that occurred at low pH and at concentration at 50 nanogram per liter close to the CMC was not endotoxic, it was biologically active. The structures formed below the CMC biological active, and macrophage assay revealed no endotoxicity in the S phases that are associated with inflammation. The phosphate residues are only towards the 6 ASU chains pointed towards the polar water surface. This is just a structure, complexity and a summary of the structural entities seen in the previous phase diagram.
Okay. Yeah, so we're slightly behind the schedule, but now we come to the last presentation of the session. And I already see Dr. Lucas Bowman here, and we can hear from him about his work on 3D printing double network hydrogens as thermoresponsive nanocomposites for dermal drug delivery. Dr. Bowman is
not a doctor yet. I'm still doing my PhD.
no problem.
So as you said, my name is Lucas Baumann. I'm a PhD researcher in the Surface Science and Nanomaterials Lab in the Department of Chemical Engineering at the University of Waterloo under Dr. Boshin Zhao. Okay, so for the motivation of this, I am sharing. Okay, so you can see the proper screen, right? Okay, good. So the motivation for this is typically hydrogels are made through casting, and this is an issue as you can get strong hydrogels, but the geometry is very limited. And we also saw a previous presentation in this group where in this functional composite materials where they did 3D print hydrogels. But part of the issue with the original like extrusion 3D printing is they're more limited in your resolution. And typically 3D printing also, you have weaker hydrogels compared to casting. And recently we've seen a lot of improvements in resin-based 3D printers over the last 10, 15 years, and also a significant decrease in cost. So what we wanted to do is make a resin that's a smart resin using sodium alginate as a reinforcement that you could make as a resin and printable in a lot of consumer grade materials. So all you had to do is provide someone with this resin and they could make smart wound dressings, which is what this comes to, patient-specific wound dressings. So we wanted to design a resin that polymerizes into a hydrogel precursor, and then by swelling it in a calcium salt solution using the sodium alginate converting to calcium alginate, you created a flexible, durable hydrogel, and then we could load it with hydrophilic drugs to be delivered dermally. So the first difficulty with this is sodium alginate is really only soluble in water, and it's quite viscous in water. So what we did first is we dissolved the sodium alginate in a water solution with dimethyl sulfoxide, glycerol, and sodium chloride. And then we evaporated the water in a rotavap. And what this allowed us to do is disperse the sodium alginate in the glycerol dimethyl sulfoxide mixture after removing the water, because the glycerol allows the sodium alginate to dissolve in a glycerol solution, while if you try to just dissolve it in glycerol, you can't. So you end up with a very smooth, almost paste. And then to this, we add our monomers and then CNCs and the photoinitiator to create our double network hydrogel precursor that's then swollen in calcium chloride to cross-link the sodium alginate networks. So here we have a description or a figure that shows the different states of the network at different temperatures. So initially it's fully swollen, and then at 20 degrees centigrade, we have the LCST going above that of the pluronic P123, which is a polyethylene glycol, copolypropylene glycol, copolyethylene glycol, or it's a block copolymer. So it's polyethylene glycol, polypropylene glycol, polyethylene glycol. And at this point, it starts having hydrophobic interactions and it pulls the network together. So you get deswelling above its LCST. But this is more of a step rather than a gradual deswelling. And then when you go above 32 degrees centigrade, you get the deswelling from the polynipam network, and it shrinks to its final size. So it shrinks at about above 4 degrees centigrade, around 5 or 6, which is the LCST of the pluronic P123, and then above 32, which is the LCST of the polynipam. And LCST stands for lower critical solution temperature. And then we also have this cross-linked with the network, the synthetic network with the polynipam and the pluronic to polytannic acid coated CNCs, which provide some strength as well, in addition to the ionically cross-linked sodium alginate network or calcium alginate network after swelling. So one of the issues with this printing, though, is that when you're synthesizing a lot of these materials, like the pluronic diacrylate that we use as a crosslinker, you don't have a lot of material, so you can't use typical exposure tests. And this is an issue because these will take 10 minutes to an hour and use quite a bit of resin. So we developed our own exposure test that prints 2 base layers that are totally flat and 50 micrometers thick. And then after that, the 3rd to the 42nd layer are these scales. And every single layer, it removes one of these scales, but instead of raising and lowering every single one of the layers, it stays steady. So you end up getting sequential exposure of each of the scales. So the first scale would be 1.2 seconds, and then the second is 2.4, 3.6, so on, all the way to 48 seconds. And this allows us to test a wide variety of exposure times without having to do multiple tests taking days and using quite a bit of resin. So here's an example of one of the exposure tests. And here we can see around 30 seconds is where it starts showing the best resolution or good resolution. And then the best is around 40 seconds. So in the second and or 4th and 3rd rows. And then what we also did was brush this with ferric chloride just to start polymerizing the tannic acid present in the sample and getting that to polymerize on the CNC. So you have a bit more contrast to see what these actual scales look like that you can read for the resolution. So next we have the fabrication capability. And so this is a 3D model that's available for free online through the resin company Amerilabs. And what we did was we used this to test the resolution of the hydrogel precursor resin because it has a lot of overhangs, thin members, and things that would be difficult to print through extrusion-based printing. And so here's an example of like the actual printed part. So it's quite small. It's only about 30 millimeters long. And so we swell this in ferric chloride for 24 hours and then bring it down to shrink it at 40 degrees centigrade and then swell it again in calcium chloride for 24 hours. And we get our final swollen hydrogel. So here's the thermoresponsive capabilities of the hydrogel, where we can see that it goes from 100% relative volume down to 79% or so, or 75, and then 59 at 40 degrees centigrade. And on the right, we can see what the samples actually look like at 20 degrees and 40. Next, we have SEM images of these samples. So we can see at 4 degrees centigrade, it seems quite a bit more swollen. And then at 20 degrees, it's less swollen, more porous, and then extremely porous at 40 degrees, where it's fully deswollen and expelled as much water as it can. Next, we have tensile measurements. And here we can see that at 20 degrees, we're getting a tensile strength around 60 kPa. And this is still a little low, but it's higher than the 4 degrees centigrade, which is unmeasurable. But typically we'd be looking at using this between 20 and 40 degrees centigrade. So the 20 degrees shows 60, and then the 40 degrees shows up to 200 kPa, which is quite reasonable for a hydrogel like this, though it does vary a bit due to imperfections in the 3D printing. So that causes a lot of variation in the measured strength of these samples. As for applications of this, we're looking at wound dressings, or as I talked about before, where you could choose the drug that you wanted to put for a injury. So you would scan the injury, print a Band-Aid for it, and then, or a wound dressing, and then load it with a hydrophilic drug. Another option is to do cell scaffolds, where you would print a 3-dimensional scaffold that better mimic the human body. And then you can grow the cells on it. And through the swelling, as you cool down the temperature, the cells are more likely to de-adhere, which we've seen a lot with polynipam. And this would allow you to collect the cells and then do something like flow cytometry. So if you're measuring cell death as when exposed to chemicals, you can expose them in situ like this, and then get them to be removed from the scaffold and actually properly count them. And then in addition to that, we're looking at drug release studies and looking at the conductivity of the hydrogel versus temperature versus strain. So at various temperatures, 4 degrees, 20, and 40, straining it and measure the conductivity at different strains, because this is a conductive hydrogel as well. And then also further characterization of the monomers and oligomers. Thank you for watching. I'd like to thank my supervisor, Dr. Boshin Zhao, as well as my co-op, Songbo Kui, for helping with a lot of the testing during the spring term. I'm open to any questions, or given that it's pretty late, thank you for listening.
Thank you. So unfortunately, we are a bit late into the session, and it will be best for us to have more communication through emails or maybe discuss right when everyone is here at the conference. But we may have to just close this session now. And last but not the least, let's thank all the presenters for their wonderful presentations and sharing their knowledge with all of us. And on behalf of the organizing committee, I would like to thank everyone for joining today. Thank you very much. Take care, everyone. I'll just stop